Okay, so let's start our lecture today. Okay. So yeah, let's finish the proof of this Corey 10.4.7. Okay. Okay. So let me draw this diagram. Okay. Okay. So remember last time we have this x tilde, and then we have this Corey projection map gamma. This is the space x. Reduced by the sorry. Okay, so this is just x. Okay, so this is x is a locally x is a candidate, locally similar candidate, locally combined Hausdorff. Yeah, and then this okay, and then this is the okay. So this is the map. Um, okay, so here, okay, so here, so okay, so we have this gamma. Okay, so this vertical gamma. So this is a subgroup of uh, subgroup of the pi 1 of x naught. Okay, so this is the point x naught here, and then okay, so okay, so so here there's a map. Okay, so this gamma quotient by the relation acting by gamma. Okay. Yeah, so I think this is the action we talked about last time. So basically you have a loop here, and then that corresponds to the action of the current space by the unique lifting. So basically it acts to any, so any point is being mapped to the endpoint by the path. Okay. Okay. Wait. What happens if you have a different point? Subgroup of. Okay. Okay. So. Subgroup of pi 1 x naught. Okay, so I'm not sure how this group. Group. Oh, okay, I see. Okay. Okay, yeah. So this is the okay. So this is the map induced by the. So, yeah. So this is the map. Yeah. So remember, uh, it's the first theorem that we talk about, right? So there's a 1-to-1 correspondence between the pi 1 of x naught and the pi 1 of the pi 1 of the space. The pi 1 of the space based at a point is there's a 1-to-1 correspondence between the pi 1 and x naught and then the deck transformation group of this gamma. Yeah. So this is the action. Okay. So this is the action by identifying the pi 1 with the deck transformation group. Okay. Oh, okay. So it's given by. So okay. So the identification is given by. So basically, if any element in this stack transformation, you map it into the. Okay. Okay. Yeah. So yeah. So basically, the idea is that. Yeah. Okay. I think I talked about it several times ago. So I just. Yeah. So we will use that later. Okay. So I'll state it while I use it. Okay. Yeah. So there's a map between the pi one and also the depth transformation group. Okay. Okay. Oh, sorry. Yeah. So there's a map. Okay. Yeah. Okay. All right. So this is a group action quotient by this subgroup gamma, and then we have the quotient space as. Let's see. I think it should be gamma. This is space, right? Okay, so this is called sorry, this is called x hat. Okay. 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 So now what do you want to show? So. Okay, so up to equivalence of covering space, there is a unique connected covering. Okay, there is a unique connected covering space such that for some point, okay, the up to equivalence time there is a unique connected covering space. X gamma hat from x hat to x such that for some point x naught. Okay, so there is a unique covering space. Oh, okay, yeah. So forget about everything I wrote here. Okay, so this is the commutative diagram when this gamma is the universal covering space. Okay. Okay, so yeah, so we want to show that there is a unique connected covering space. Okay, so yeah, so forget about all this stuff. Okay, so just we have the condition that this X is connected, locally similarly connected, locally counter-hostile. Okay, so we have the condition that X is connected, locally similarly connected. Locally compact household space. And then we have the x naught in x. Okay, and also okay. So then up to equivalence class of the covering space. Okay, so there is a unique connected covering space. Okay, so I want to show that there is a unique. Okay, so I want to show. So there is a unique up to equivalence class. Okay, so unique. Connected covering space. Gamma hat from this x hat to x. Oh, okay. So such that okay, so for some point. Okay, x naught in this gamma hat this covering projection map, the push forward of this covering projection map maps the pi 1 of x hat with x dot hat to pi 1 x dot maps. Okay, so maps pi 1 of x hat x dot hat isomorphically onto okay. Okay, I don't okay. Onto this group gamma. Okay, so namely you have a covering projection such that the push forward of this pi 1 x naught. So this is the base x naught, and then you have the x naught hat, and then yeah. So the push forward is onto this subgroup. Okay. Okay, let's show the existence of this this gamma hat. Okay, so I think let's see. Except your locally semi-connected self-automorphism that add property discontinuity and freely and student, and then let this be the corresponding that simply connected, locally compact hostile space. Okay. Okay, so basically by the we showed last time that by the 10.3.3, okay, the existence of universal coverings. So so this x, okay, so this x, okay, okay, so since this x is so since x is connected, okay, so so connected, locally simply connected. So okay, so theorem, the 10.3.3, which is the existence of universal coverings, implies that so there exists a universal covering space okay, so let's call this gamma from x squared to this x. Okay. Let's draw a picture. So so let me erase that. Okay. So this is this is the second part of the theorem. Okay. So the first part is so here you have the universal cover. Okay. So then let's see. Okay. So So, oh, okay. Simply connected. Okay. Wait. Wait, that's simply connected. Nice. Okay. Wait. Okay. Okay. So let's see. Then. Okay. So it says theorem 10.4.6. Construction of a chorion from a properly discontinuously free group action. Okay. So 10.4.6. Okay, so this X tilde is, of course, it's a universal covering space, so it is simply connected, right? And then, so I think let me check. I think simply connected implies locally simply connected, right? Because simply connected, you have this path connected, and then the pi 1 of pi 1 is trivial, right? So pi 1 x naught is trivial. Okay, let me try to verify. So, X is path connected. Okay, path connected implies, okay, locally path connected, and then, okay, pi 1 x naught is equal to the, okay. Okay, so why there's a neighborhood? Oh, okay. I don't know. Okay, so why is local? So if you have a, okay, so let's try to see. So X simply connected. So we want to show that, so implies simply connected, so it implies locally simply connected. Okay. Okay. Oh wait. Okay. Okay. So now that you okay. So so let P be X. Okay. And then U be a neighborhood of X containing P. So it can be a neighborhood of P. Okay. U containing P. Oh, yeah, that's neighborhood of P. Okay. And then okay. Okay, so we want to show that there is simply connected neighborhood. there is a simply connected neighborhood V of P U. Okay. Why there is a neighborhood? Wait. Oh, wait. X is simply connected. Oh, wait. Okay. Oh, okay. Okay. So because this X is okay. So we know that this X is connected, locally simply connected, right? Oh, okay. So this implies that because this X is locally simply connected, so and also by the property that wait. Okay. Yeah, I think this is not enough. Okay, I think this is not enough. So okay. X tilde is simply connected. Okay. And also we have that oh wait, shit. Okay, we also have that. So and this X is okay. And okay, so yeah. So maybe let me just say this. So we want to show that this X tilde is simply connected. Okay. So want to show this X tilde is locally simply connected. Okay. Yeah, so simply okay. Okay. You'll be a neighborhood of P. Okay. Okay. Okay, so what we do is that, so this P is the X tilde, right? So yeah, what we do is that we project it down to, yeah, so we'll pick a point P in this X tilde. Sorry, let's call this P tilde, okay. And then this U tilde, okay. And then let's do a projection P, okay. So yeah, so now let's call this neighborhood U, okay. And then what we do is that we pick a, yeah, so we can always do that, right? We can pick a, let's call this U prime, okay, be a evenly covered neighborhood, and then you take the unique, let maybe U prime tilde be the unique component that contains P prime. Okay, and then okay, so because this X tilde is locally simply connected, right? So you can also just replace this U prime by the simply connected set. You replace this U prime by the locally simply by the simply connected open neighborhood that contains this point P. Okay. And then you take the, so this is like a locally simply connected. So this is simply connected, okay. So the question is, and then this is a homomorphism. So the question is whether you have a homomorphism image of a simply connected set is still simply connected. I think so, right? Because yeah, you can just take the, I think it is simply, yeah. So basically, if you take any path, right? Take any path, and then you